right, so let's get started. Today, we're very happy to have Shirley Ho visiting us from Carnegie Mellon. Shirley did her undergrad at UC Berkeley. She then went on to do a PhD at Princeton, Davis Fergal. She graduated in 2008. Then she was a Seaboard Fellow at Lawrence Berkeley Lab. And then in 2011, she joined faculty at Carnegie Mellon, and she's been there ever since. She's very active in large-scale structure and large galaxy surveys, and today she's going to tell us about BOSS.
Hi everyone. The last time I was here was probably 6 years ago, probably when I was graduating grad school or something along those lines. So that was a while ago. I was supposed to come back many times and always failed because it apparently cost $1,000 to get here from Pittsburgh, which is 1 hour away on the airplane. So I hope to hopefully tell you a little bit about BOSS. And if you have any questions, just let me know. Any time of the talk, feel free to interrupt. I know CITA has a very strong interruption culture, so I'm sure that will happen. And the work I'm going to talk about today is with Martin White, Anthony Pullen, Shadab Alam, and Mariana Vargas. Martin White was actually my Berkeley undergrad advisor, and now we kind of work together, which is kind of nice. And Anthony Pullen is a Williams Fellow at Carnegie Mellon right now, and Shadab Alam is a graduate student at CMU. With me, Mariana Vargas just moved from CMU as a postdoc to UNM as a faculty. So all this work cannot happen without the BOSS collaboration, obviously, and I will tell you how to learn to love the BOSS. BOSS here could be many things. Could be this one for those who are very familiar with American movies, or not so familiar, hopefully. Or the more recent TV series junkies would also recognize the Madam Secretary, which is based on apparently Hillary Clinton. Maybe this is the future BOSS for America, maybe not. We don't know, hopefully not the other ones. Anyway, so BOSS for me here is this guy, or this girl, whatever. It's a telescope. If you look onto the right side, it's the White Sands Missile Testing Range, which is actually a gorgeous national park, but it's also testing missiles. On the left-hand side, just straight highways of Texas, which is not super exciting. But it does really cool things. It's a 2.5-meter telescope in New Mexico. It has collected 1 million spectra of galaxies, 400,000 spectra of supermassive black holes, basically quasars, 400,000 spectra of stars. These are actually failed quasars. Well, I shouldn't say failed. We try to target and find quasars, but then they happen to be stars because we cannot select all quasars. And the images of millions of stars, galaxies, and quasars. And I'm going to use some of these stuff to learn about the universe and hopefully tell you a story today about how to learn to love the BOSS. So what does it do? We'll talk about baryon-acoustic oscillations, which I'm sure a lot of you know, so I won't give too much introduction, but just a little bit, and many others. So what are the many others, which I list just to impress you? There's so much more that I did not list. But just to go through a little bit of it because they're closer to what I do, probably modified gravity with growth of structure. Growth of structure really just means here using something called residual space distortions, which are basically the galaxies are moving because of peculiar velocities, and that help probe basically the spatial metric of the universe. And that's how you can probe gravity because you're actually probing the metric directly. And then probing initial conditions, neutrino masses, using the whole shape of the correlation function or the Pao spectrum, the Fourier transform of that. People have done this before using even photometric data sets. And they put actually really good constraint even before Planck came around. This was at 0.23 eV. That was the upper limit at 99 percentile, I think. And that was before, this is pre-Planck. This is WMAP, with the galaxy data set. So just to show you that it's actually very competitive. How about finding missing baryons? For those who do a little bit more astrophysics-ish, we know that we're missing some huge chunk of baryons in the universe. And I was trying to do it a long time ago, and now we finally are starting to be able to do it with the new ACT-POL data for those who work on CMB. You use something called kinetic Snell-Sodova effects, which are looking at the electron density of galaxy or the clusters, depending on what you're cross-correlating with. And it's only possible because we actually can reconstruct the velocity field by using the density field of the galaxies. I won't be going into this, but you can ask me later on if you're interested. Understanding intergalactic medium and dust in the galaxies or even quasars. Breeze was here as a postdoc, and I think he stacked a lot of different galaxies or quasars together and tried to see what are the changes caused by possibly dust because they become more redder. And galaxy cluster evolution that you can probably guess. And I will be talking about this, which is a new way to test gravity using lensing and BOSS, or any logical structure surveys. So what is really BOSS BAO? There's a very simple outline for today. Can we improve what we're doing right now? What do we actually learn from this? I will make a quick introduction what it is. What other science can we do with BOSS? As you can tell, there's so many. And I'll just introduce a new probe that nobody's done before, that we can learn about gravity at the larger scales that wasn't touched before. OK, so what's BOSS BAO? So pairs of galaxies are basically slightly more likely to be separated by 150 megaparsec than 120 or 170. That's basically the idea. It's the same little circles that you will see if you stack C and B. So cosmic microwave background, if you stack them, they will actually have the similar circle with the exact same scale. This is basically imprinted from very, very early on from the last scattering surface, but it's on the baryons. And it evolves forward and becomes the galaxies now. So that's why. These effects are highly exaggerated in this picture, even when it's less contrast after the projector shows up. We actually don't see such nice rings in our actual data. The distance of this 150 megaparsec is very accurately computer calibrated from the anisotropies of CMB, because these are the rings. If you stack the Planck data 2015, you will see the rings. They're exactly the same scale here, and as things grow, nonlinear structures evolve, we actually can observe at multiple different epochs the same ring over and over and over again. And so in Sloane 3, Sloane Sky Survey 3, which BOSS is one of the 4 flagship projects, we used the map of larger structure in the universe to detect the imprints of these sound waves. We used 3 different tracers: galaxies at redshift 0.2 to 0.7, quasars from 2.1 to 3.5, so supermassive black holes, intergalactic medium as revealed by something called the Lyman-Alpha forest at redshift 2.1 to 3.5. For those who don't work on Lyman-Alpha forest, it's very simple. It's just the shadows casted by neutral hydrogen on the photons from supermassive black holes as they come to us. And so it tracked basically neutral hydrogen of the universe. We track the dark matter density. So we're looking for an excess. And Andres Loza has given a lot of talk, I think even here, about the Lyman-Alpha forest. So you should probably know about this. And we're looking for excess of clustering of overdensity regions separated by 150 megaparsec. So again, this idea of looking at it. And a slice of BOSS, you hope you will see something like this. But honestly, this is what we actually see at redshift 0.2. There's very little structure in it. There's no circles as far as you can stare. It's a very, very, very small effect, super hard to detect. And that's why you need huge volumes and a certain number of densities. And there's a balance between the two so that you can get a reasonable signal to noise to detect the BAO. It's an extremely hard effect to detect. But we can do it. The clustering analysis of the BOSS galaxy sample produced world's best detection of the late time acoustic peak. The early time one is detected by Planck. So that's the best detection with the early time acoustic peak. We have the best detection of the late time acoustic peak, which is the baryon acoustic oscillations. This is it. It's exaggerated because it's r squared times the galaxy correlation function. So exaggerated how big the effect is. If you look at the actual effect, it's a tiny blip without multiplying by the r squared. It's 150 megaparsec. And this number is the one that you actually kind of this will change as you think that the universe just has a different cosmological parameters. Does that make sense? OK. So what is after reconstruction? Anyone knows about that already? So I don't have to talk about it? Nobody. OK. After reconstruction. So this signal was actually more like this before reconstruction. Reconstruction is a way to move the galaxies backward to undo the nonlinearities that basically smears out this little peak. So the peak was like a little blip before, and as galaxies and things evolve forward nonlinearly, it smears out the effect. And we want to move things backwards. And that's why this reconstruction technique actually makes a sharper peak that we can increase the signal to noise of our baryon acoustic oscillations detections. Any questions? I'm going to pause here because everyone looks a little confused. Sorry, say that again? That's a really good question. I'm actually going to come to that a little bit later. But basically, this fitting line right now is not an actual, well, there is a model to it, but it's actually not any of the theories that you probably heard of. It's a combination between a linear perturbation theory, sort of first order Scotch-Amaro type, plus a little blip that you add on top of it. But I will actually talk about why people do that. The reason why we don't have this as a theory right now, actually, is because nobody has so far, which I'll come to, produced the correlation function post-reconstruction, theoretically. So if I asked you to produce post-reconstruction redshift space correlation function of galaxies, that's not done until very recently, which is I'm about to get to. Okay, so I asked multiple people, like, can you do that? It's actually hard. Because the work of reconstruction actually we're moving, so you move things forward, you evolving things forward very nicely. And then we do this linear evolution backwards a little bit. So they're not really what you know as what you think of linear correlation function. So this data points cannot be fit by just linear correlation function. Does that make sense?
You said that you don't have a good sense of the, you cannot calculate theoretically the post-reconstructed, but you know the pre-reconstruction if you run a simulations. But you don't know how to evolve that.
You don't know how to bring the simulation, well, okay, you don't know how to do a theoretical predictions of reconstructed correlation function until the next paper I'm about to show you.
Okay. But somehow you can do the reconstruction.
We're doing reconstruction, which is a technique on the data. So the data set, what it does is actually you take the field of the galaxies, you get the overdensity field, right? So subtract the mean and all that stuff, divide out the mean, and then you calculate the potential well. So if there's a potential well, it just does the linear order falling into the potential well, right? So you just go backwards in time, and that's the data points afterwards. And there are about 3 different implementations. They all give about the same answer in the correlation level at the summary statistics level, like the correlation function, monopole, quadrupoles. But the actual positions of the galaxies afterwards are different. So it's actually a pretty hard question. But I'm going to give the answer very soon, unfortunately, because I think we actually are doing it right now. It's not perfect, which I'll show you. The peak location is a very good question, so keep the questions coming. The peak location is measured to 1% in our high redshift sample and 2.1% in our low redshift sample. So that's really cool. But can we improve the analysis? So that's the part we kind of hit on earlier, which is that a theory plot, right? So is that line a theory line? It's not. What I show you is not a theory line. So we cannot predict. As of early 2015, we cannot predict the post-reconstructed correlation function in redshift space for galaxies. And so the idea here is that we have a full 2D correlation function. It has information on the BAO, which is, if you look at, smear out the little blip into 2D, that's along lines of sight. That's perpendicular to lines of sight. That's actually the BAO peak. You can see slightly squashed in the large scales because of the redshift space distortions I mentioned earlier. The peculiar velocity is moving things around. So the galaxies' redshift are actually slightly different from what they actually are. So when we observe, they slightly squash. It's not completely spherical, as you can tell. And if you do a Lagrange polynomial transform, you get a monopole and a quadrupole, right? So the monopole is this nice peak that you would kind of expect it. This is times r squared, so it exaggerates the effects. The quadrupole is non-zero, as you expect, because of this redshift space distortion effect, which is very useful because it constrains the growth of structure, that constrains things like modified gravity, anything that probes the spatial metric of the universe, right? So anything that affects the metric, the spatial metric, it can be probed by the growth of structure. So we do the reconstruction, as you saw earlier. Take this monopole quadrupole, You pass it, well, actually don't take this directly. You take the actual data set, and what you do is that you want to go from the red curve to the black curve. So that's what reconstruction is doing. It basically boosts the signal in the monopole. But at the same time, it reduces the power in quadrupole. These many lines here shows you different implementations of reconstruction. So different implementations actually give you a slightly different result. That's the original quadrupole, which is the same plot as here. And if you do different ways of reconstructing, you actually get slightly different quadrupole. And don't forget, the quadrupole is super useful in getting rational space distortions, which probe the growth of structure, which probe things like modified gravity, or however things that affects the metric. So my question here was, well, but we want to do all that, testing gravity, testing all kinds of stuff that was change the metric. So right now, what people do is that we fit the reconstructed BAO completely separately from the rational space distortions. They use different models, and the stuff we quote from the post-reconstructed BAO will be merged at the likelihood level at the very end of the analysis. So it's not even related when they do the analysis separately. They have different teams who fit the reconstructed BAO and RSD completely separate, different theory models, different linear theory or perturbation theories. Number of fitting parameters about 15, even just at the BAO reconstructed fitting level. So if just to fit this, it's about 15 fitting parameters, just to give you a sense. So it comes to this easy question, is like, well, can we fit both of them at the same time? Both the post-reconstructed BAO and rational space distortions. So that's the idea that we're trying to improve the analysis on. So very complicated plot. This recently came out from Mar and White's paper. And on the y-axis is the monopole and the quadrupole multiplied by r squared. You flip the quadrupole here so that you can see them in the same plot. This is the distance. Let's concentrate on the squares and the diamonds. The squares is pre-reconstructed from simulations of halos. So now this is all halos. There's no mess from the data. Diamonds are the post-reconstructed of the halos from simulations. And then you turn it into correlation functions. So everything is OK there. And then Mar and White has come up with this theory that uses Sadovich approximation that fits pretty OK, I would claim, both the pre-reconstruction lines, as you can see, the solid line, the pre-reconstruction for the monopole and the quadrupole, and the post-reconstruction, the dashed line. And you can see that fits the diamonds quite well. You see a boost in power at the peak at the monopole, which is what you expect. You actually want to see the squares going to diamonds like this. You actually want to see this line going to this dashed line. They're not exactly perfect yet, as you can tell. And this is something we should still work on, but this is the first time people even try, or even try successfully to do this. And the quadrupole is deliberately non-zero. We do not remove the quadrupole in this post-reconstruction method. So it is reconstruction method. So the way we do the reconstruction here is different from the standard one. And we actually keep the quadrupole. So we can do the rational space distortions analysis as you wish. And the theory predicts both the monopole and the quadrupole properly with all the pre and post reconstruction. So that's a very important part. It's not perfect, but I think we're getting pretty close. And I'll show you why. New reconstruction method basically retain the rational space distortions part of the story. The new reconstruction method also boosts the signal to noise for the BAO peak, which is very important. And it's a good fit preliminary simulation of dark matter halos. This is all dark matter halos. There's no galaxies here, OK? So we did something more. Because we want to put it in galaxies, we put in survey selection function, which is a lot of mess. And we basically try to fit.
Sorry, before we move on.
Please.
So the delta approximation now is going to be your fitting function. So you're fitting it.
Can you say it louder?
Sorry.
Sorry.
The delta approximation, you're going to try to fit to your data through your post-reconstruction. So how many parameters are being used? Is this just a nicer way of fitting?
It's using 4 parameters. Actually, it's this slide I'm about to say. Okay. There are 4 parameters. Where did I say it? Here. So there are 4 parameters to vary: the peak height, which defines large-scale bias, to 2 distance scaling parameters, alpha parallel, alpha perpendicular, which basically say where the BAO peak is at different directions, and the parameter containing the effective field theory terms, which is just 1 parameter, controlling how much we put in. And we hold the linear theory power spectrum fixed using input to the simulation. So this is a simulated survey simulation. Actually, there are 1,000 of them that we average over. And we hold F fixed for now because of the survey we're using does not actually generate F that nicely. And we use a particular smoothing length for the reconstruction method. So the smoothing is required when you turn basically this very sparse sampling of the density field to a density field before you do the reconstruction. So we do all that. And we fit the pre-reconstructed multipole, which is the monopole and the quadrupole, with the Sadovich approximated theory. Pre-reconstruction, the distance ratios are expected not equal to 1, but close, because of nonlinear evolution. It should be slightly off, not exactly, due to just the fact that things are moved around because of nonlinear evolution. That's what we got for alpha parallel, alpha perpendicular, in the 2 directions, along lines of sight and perpendicular lines of sight. If alpha equals to exactly 1, you know that the universe is exactly what we put in. That's basically what alpha is, for those who don't do this. And the next part is post-reconstruction. You bring it back to where it's supposed to be. So it should be exactly 1. That's what we should see, and that's what we got, which is, we were very happy when we saw that, actually. The 0.999 and the 1.00. That was actually significant figures that we can get. Using the Sadovich approximated theory that you saw is not even super perfect yet. But this we are pretty happy about. So right now we want to combine both the BAO and RSD fit in one shot. Basically allow using BAO reconstruction and fitting the RSD in one swoop, not separating them, doing different parameters, different theories. And the fact that we have a unified theory model that predicts both the monopole and quadrupole pre and post-reconstruction. The post-reconstruction part is the hard part to predict. We have unbiased recovery of the distance scales, which is important because it says what you're doing is more or less correct. And there are very few parameters that we need to vary. It's only 4 different parameters that we're actually varying, especially compared to the traditional BAO fitting schemes, which we do use in BOSS, like as right now. So we're hoping to do all that with Sloane final data release hopefully coming up, DL12. So what can we learn from this? So what I'm going to show you later is the parts that we actually already published from BOSS from the last data release. This is some of the stuff we can do, like constraint cosmology, which is, I think everyone knows about. The omega matter density in the universe, sigma 8. If you start from the very big swath, which is the Planck 2015 plus the weak lensing, that's actually what you get. And if you go to the next biggest plot, it's actually the gray one, which is Planck plus BAO and RSD analysis. And if you add weak lensing, it actually doesn't really change the contour very much. And if you add everything, which is BAO supernova and Hubble parameter, you get the really large shrinking for the parameter right there. And there's combined constraints, of course, on things like dark energy. This is the equation of state at 0.266. That is the time dependence of the equation of state of dark energy. And if you look at BAO plus Planck itself, it's actually quite off. But if you look at the total constraints, is probably something like close to the cosmological constant. But so for someone like me, maybe slightly more optimistic, maybe there's a hint of something slightly different. We don't know. There are some tension and comparisons that we made with other probes. Just for, really curious for us is to look at how different are different probes measuring. And they're supposed to be doing the same thing when you think about it. These are different cosmological models on the y-axis. On the x-axis actually shows different probes. They constrain different parameters, right? So on the leftmost plot is lensing and cluster. Residual phase distortion is the center. Laminar force 1D power spectrum on the right. The black dots are Planck plus BAO plus supernova, I believe, yes. That's what Planck plus BAO plus supernova predicts for each of these models. But if you look at the measurements we get for lensing and clusters, they're actually all on the left-hand side, for example, of the black dots. So there's some tension there. And then the residual space distortions doesn't have as strong of a tension, but we're starting to see, and they're actually all from the same data set, don't forget. These three and the boss BO is from the same exact data set. So they should actually have less tension. And this is Lyman alpha force 1D power spectrum. It's even on the right-hand side of the prediction. So it's kind of interesting to see all the different tensions and things going different direction and guessing, how things will work in hopefully very, very soon. So what other science can we do with BOSC? Let me just pause here before we move on to the next part. It's like talking about one other science I think is kind of cool and that nobody ever done before. So other questions about the previous parts? No? Feel free to interrupt. That's totally awesome. OK, there are many things we can do. We're not going to talk about all of them. I'm only going to introduce the new probe combining BOSC and lensing to learn about gravity at the larger scales. But feel free to ask me about any of the others. So we call this probe you've probably seen before or maybe heard of before. For someone who's younger, you've probably never seen this because it's from 2010. It's a probe that basically is bias-free probe of gravity, combining galaxy clustering and galaxy lensing. Reyes et al. 2010 with Mandelbaum and Sarjak, and I think a couple other people have done it. It's a Nature paper. It probes gravity using this U of G parameter as a function of scale to about 40 megaparsec, from the smaller scale to about 40 megaparsec. And you can, in principle, rule out, this is GR plus MLC at that time. FFR gravity, TAFIS is actually ruled out because of that probe. So, but what does it take to do this analysis, right? It takes a spectroscopic galaxy observations with high enough density to produce residual space distortions. Not very easy. Photometric galaxy observations with good enough seeing to do weak lensing of galaxies. Also not so trivial. As some of you, if you work on lensing, you'll probably tell me. The lens plane of the lensing measurements need to overlap with the spectroscopic measurements significantly, not just a little bit. And so far, it's only repeated once by Blake et al. 2015 due to lack of suitable data sets. This is just actually a couple weeks ago by Blake et al. Using BOSC data sets with CFX TLS lensing. So we sat down actually a while ago and looked at the drawing board again and say, OK, can we go backwards and say, what actually can we do with this probe that people haven't really thought about before? So we want to probe the gravity. We want to probe the metric directly. So that's the metric we wrote down. And the two things that we actually want to look at is basically non-relativistic particles feel the gravitational potential. So the motions of these particles probe the dynamical mass. While photons, like relativistic particles, are deflected by the spatial curvature. So it probes different parts of this E of G parameter. And if you don't want to see the equations, that's fine. Because the GR version is fairly simple. These are the relationship of all the parameters in GR. And if I modify gravity and just slide in these functions, this mu and gamma in here, that's what modified gravity, if you want to modify it in a certain way. And U of G becomes something fairly simple, too, at this point with modified gravity. So it's a very simple, also important thing is it's bias-free estimator for something we can probe the gravity. And just to get you a sense of the spatial and the temporal dependence of U of G, this is what general relativity does. U of G as a function of k and z, mu equals to 1, gamma equals to 1. This is what FFR gravity does. It has a frequency dependence that's pretty obvious. And chameleon model has a different frequency dependence, different residual dependence, actually. And what we're trying to do is that, well, we're writing equations a little bit to something we, like observers, I will call myself observer right now, to really understand what's going on. We write it is actually tracer lensing, correlations, residual space distortions, and tracer-tracer clustering. Fairly simple here. But we can use CMB lensing instead of galaxy lensing. It's very simple. It's a very simple switch. But it means it's something important. Why is that? Why does it matter we use CMB lensing instead of galaxy lensing? Well,
so when you say like FFR gravity,
yeah.
do you have like do you limit to like FFR gravity such that it explains the accelerated expansion, or?
It's actually pretty free here. So this is the generic expansion using Alexandra-Silvestri's normal parameterization.
Because like FFR is like a arbitrary function, right? I'm just wondering why this is that simple form, like for any sort of FFR.
Oh, so you mean like really, really wide. I think this is pretty general, and we have also assumed that it has satisfied some nearby like solar system test. So there's some constraints on it, but I don't remember exactly which constraints we talk. Okay, but it's pretty wide. If you just do FFR, it could be very general. Okay, so we're writing equations for this part. We want to change it to CMB lensing instead of galaxy lensing. And why does it matter? It's actually quite important. This is what you usually do. This is what redshift on x-axis. Y-axis is all the large-scale structure surveys that I can have access to, hopefully now or in the future. And this is the lensing source population. And these are lens population. This one is quasars. I'm including them, but there's nothing behind it to use as a source population right now. But if you put the lensing source right here, which is at redshift 1100, everything else becomes a lens. You can do it right away. We know the CMB lensing kernel actually peaks very nicely, overlapping with all the other large-scale structure surveys at about 1-ish. We know the photo Z basically off the lens source exactly at 1100. You don't have to do any photo Z of galaxy lensing anymore because it's really not so trivial. And we don't have things like intrinsic alignment of the CMB because CMB is very simple and very clean. The unlensed CMB is extremely easy to think of. It's Gaussian. So no astrophysical systematics that we don't actually know. And we're working on testing a lot of different systematics, but nobody else have really looked at this before, so I feel like superheroes because there's no man's land out there. So why is this probe so cool? I just want to mention this because people don't really realize this. This is the tracer CMB lensing, gives you a factor of B, which is the bias, which relates the galaxy or any tracer to the dark matter density field. The redshift space distortions give you a 1 over B, while the tracer-tracer clustering gives you B squared. So if you do all these cancellations, you notice that this probe is bias-free. It has very little dependence on the astrophysical relationship or assumptions we have to assume between the tracer and the underlying dark matter density. And now what we could do with the CMB lensing is that it just will reach to very large scales that we've never done before. So let's take a quick look at how plausible what I just told you. Is it just Kool-Aid that you're drinking?
Sorry, is this bias-free generally or bias-free under the assumption of linear bias?
So that's a very good question, and we actually got that quite a lot. So this equation, like the stuff that we've done all before that, can be generalized to be all kinds of bias. But then what we assume here in this equation requires some linear bias assumption. When I say this bias all cancel out. However, we do check for nonlinear biasing and stochastic bias in our analysis, even with this equation. So that's actually the one systematics that we actually have to pay quite a bit of attention to. So we use a lot, like 100 simulations to check that and make sure we didn't miss that.
Stochastic bias, you get anything, isn't it? With stochastic bias, anything goes.
That's also true. So we only use, I should say we only check the nonlinear nonlinearity in that parts, not like really crazy stochastic bias models. But we can definitely talk more about this. But I can show you a little bit more. This is just looking at how plausible it is by looking at various different surveys we considered. BOSS that you heard of, Dezzy is something that with 14,000 square degrees with gigantic number of galaxies and quasars. Euclid W1 that you probably heard a little bit about recently. Anyone who heard of W1? I just worry that this is the Canadian culture bias.
Question, who is not heard of it? Because nobody's ever raising their hand. So if you ask a positive question,
who hasn't? Okay, who has not heard of W1? They're not going to raise their hands. So everyone's heard of W1. Okay. Anyway, so we maybe they're just not raising their hands anyway because that's. They will do the same thing every single time. The properties various galaxy for photometric surveys LSST. Euclid and Dezzy also have photometric surveys. Actually, W first too.
What's the time scale for Dezzy?
Dezzy is actually, I'm actually a co-chairing of the larger structure there. Dezzy is actually happening very, very soon. We are having a commissioning run at 2017. So commissioning camera. So it's not a real Dezzy camera, but it's just very much a commissioning camera that we're testing things out. And then we just went through CD2 for those who are familiar with the DOE lingo, which doesn't really mean anything. But it means if you pass the CD2, Department of Energy in the United States will fund you, for sure, for future. So we just went through that. Actually, last week we'll hear it back, like anytime.
And so, but it's in that goes when
2018.
survey completed in 2018?
Starts at 2018.
When is it
Complete in 4 to 5 years. So I would say 5 years just because you're doing all this other stuff. But the plan is 4. Okay. You probably heard of Euclid and W first. I will talk a tiny bit more about this, but feel free to ask questions because I don't know how much people know. How do we do current surveys? So that's where I said I was data point. That's E of G, and as a function of redshift. That's the one data point we had before. Chris Blake actually put a data point right around at redshift 0.5 recently. We should put in. And we can do that with CMAS and low C, we realized, with CMB lensing. All the previous ones are with galaxy lensing. So we probed up to 42 megaparsec before with Reyes et al.'s measurements. And they cannot use anything in small scale because it's actually really hard. Even modeling at 10 megaparsec is hard when you think about it for galaxy clustering or galaxy lensing. So Boston Planck lensing should be able to probe up to about 100 megaparsec. And we don't actually have to worry about all the systematics at the smaller scales, which is cool. That's what you can do with upcoming and future surveys like W first. And with advanced ACPO, for those who do CMB analysis, that's actually pretty cool, realizing that we might have something really awesome for polarization.
You're missing a line for China.
Huh? Yes.
Line for China, which has a much lower noise than any of these.
That's probably true. You need to give me some spec. We'll put it on. If you give me some spec on that one. Actually, Anthony does a lot 21 centimeter, so he'll be perfectly happy to put in 20 centimeter or intensity mapping type of lines. This is Dezzy, and I'm sure Chime will actually have a huge. Can you do RSD okay with Chime? So that's what we need. The redshift space distortions, like what's the error bar approximately for one bin?
Just comparing CMB lensing to the actual. Is that what you're doing?
Yes, this is just CMB lensing from advanced ACPO and Planck. I thought you were replacing Chime with replacing W first with Chime. That's what you're saying.
Yes, but I guess I'm missing what's being done. I said just measure the power spectrum and project. If you're doing projected cross correlation with the Kappa field, why do you care about that?
You need redshift space distortion because of that equation here. We need the beta from growth of structure probe. So you need redshift space distortions for this. So you could do it only if you have at least about 8 to 10% measurement of redshift space distortions. For photometric surveys like LSST and Dezzy.
I think you have to talk about homing. So the thing that you don't know, I think, is a different thing for things like Chime than it is for these.
Say that again, sorry.
You have to talk to a fellow named Homing, isn't it? But you have to talk to him. He'll explain to you the types of biases that Chime needs to know about. So it's a bunch of different things. It's more complicated than a bias for that. You need to know omega H1. You need to know a bunch of things that are
right. Do have all these other factors, yes.
But you don't need to know the bias. So it's a different set of things you don't need to know, but you have to go through and see what it actually does to you.
Okay. So it's probably some kind of like omega H1 combination with some other factors here instead of B, you were saying.
Yes, but
you still need the probe of the velocities, probing, the dynamical mass.
Yes, that's what homing does. So it's,
perfect. We should talk.
You go through and see if it does the same thing as what you're thinking of or not.
All right, that sounds good. We can check this. All right, so where were we? All right, so we got that part. This is what we're supposed to do if we can pull this off. Boston Planck lensing, current data set right now. That's what we can do. Future things. So we did look into Boston Planck lensing. I'll show you something. That's what we feel like going into it, for those who know the references. All right, I was having trouble with some of the different audience. That's how we felt after we do this. For those who don't know, this is Red Wedding, a Game of Thrones. And so this is what you get for actual data sets. This is CL kappa G, which is the lensing field and the galaxy view. And then that's the CLGG, which is the 2D correlation function for the C-mass galaxies, which is from BOSS. This is what we're Planck lensing. That's what the EFG plot we've seen before, except this time I do it in L space, which is angular scales. This is small scales, that's large scales. Okay, R is up there. This is small scales, that's large scales. That's the largest scale measurement Reyes et al. Has from 2010, like the largest one. We just pull the one that's at the end. And that's what we got so far. Let me just read the plot slowly to everyone. This is GL theory, which is the blue line here. This is FFL gravity with a very stringent constraints that we put on. These are EFG measurements with two different ways of estimating errors. One of them using jackknife, the other one using 1,000 marks from BOSS, and with some other things. And then we basically are able to probe gravity bias-free at scales basically never touched on before. We're going from 40 megaparsec all the way up to nearly 90 megaparsec. And we're pretty excited about it because we can also rule out things like chameleon theory that, for example, this chameleon theory is ruled out at 99% confidence interval. And that's with the current data set I already have in my laptop. And we're not even talking about things we could do with other measurements. So let me just conclude. BOSS has come of age. We can make 1% distance measurements using BO at multiple redshifts. So we can do that. We prove we can do that. We actually are trying to improve all these measurements appropriately. We can make quantitative statements of our cosmology, like what is dark energy, if we actually are able to figure out whether this is shifted or not. Be interesting. There are many interesting things in larger structure that we can work on. One of them is to think really hard about cross-correlations with currents and upcoming CMB experiments and what they actually provide us. Like, nobody has even thought about this before. And that's what we got. And looking forward a little bit, since I promised to talk about future surveys a little bit, this is Sloane Digital Sky Survey 4. It has 3 different components to it. Apogee is a galactic archaeology project that actually will even move the Sloane telescope to the south. We actually have the northern and southern part map. Manga has been going on pretty serious now, and they are basically looking at, for each galaxy, we're looking at putting on 1,000 fibers on it. So you have very interesting integrated spectrum on a bunch of stars for every single galaxy that it decided to map. There's about 2,000 of these galaxies with this multi-fiber spectrograph. And then this is eBOSS, which is an expansion of BOSS, which will go even further. This is 0, this is redshift 0.5, this is 2.5. And you can see that the BOSS gas is mostly here. eBOSS gas is going to go further. And the interesting part about eBOSS for me is that it actually going to map 1 million quasars. Trying to do quasar clustering in not small scale, in large scales, and really trying to pull that off, it could be pretty hard. And could be very exciting because you're really probing a large range of volume with very, very low density, actually. We'll see whether we pull it off. We're hopeful. And that's for Lamina Forest. That's where we're probing. With Sloane 4, which is happening right now, which I just came back from the collaboration meeting, actually. And this is Dezzy. 2018 start date, for those who were asking earlier. This is the big at redshift 0. Also probing really far. It's just a very dense map of the universe. We're talking about millions, like 18 millions of emission line galaxies. For those who might not want to do cosmology, maybe astrophysics of how galaxies form. You'll also be interesting. We also have a very interesting bright galaxy survey, which is basically take the old Sloane and just to make it much deeper. So take the Sloane 1-2 that you probably heard of before, which basically does a main galaxy observation. There's no particular selection, just go deep and just look at everything you can do. And that will be really interesting, just thinking about all the galaxy science that you can do, or quasar science you can do at that level. So I'm very, Sloane on steroids, on top of this volume mapping type of analysis. This is Euclid, which I'm also part of. And if we look at imaging about 30 galaxies per square minute, this is a little further down the line. It's 2018, I would say 2019 or 20. It's fully funded by ESA. NASA's part of it. And it will basically do spectroscopy imaging. It will go after a huge number of galaxies, very large areas, and aims to map the geometry of the dark universe with weak lensing, BAO, and RSD. Finally, W first after is this. People probably heard about this spy telescope that's somehow handed to us, and nobody who's not US citizens or permanent resident cannot even look at certain specs. You can't even have a real picture of the telescope. This is not the real picture of the telescope. We don't even know what it looks like. It's a NASA-led mission, and it just went through a lot of lobbying. I think we will know very soon whether we'll have, I think, 60 million next year to start the project. So we'll know in about a few months whether this will actually happen. Already calls had come out to ask for what kind of science you want to do, what kind of science you could do with it, and making sure it will happen. NASA's, well, this WFIRST after is not just doing cosmology. Only about a third of it is doing cosmology. The other 2/3 doing actually exoplanets and a gas observatory. Anyone can apply and just observe that patch of the sky using the capabilities, for example. So it's a very different mission. This is a plot. This is MP BAO, which shows you how well you can measure the BAO in some ways. You want it to be at least 1 to measure very good BAO. You can kind of put it off a little lower using reconstruction that I mentioned before. That's Euclid as a function of redshift. This is WFIRST with 2 different emission line galaxies, population H alpha and O3, oxygen 3. And this is the imaging improvement of after over Sloane, or LSST over Sloane. This is Euclid with very wide bands. So it's interesting to look at how, comparisons between Euclid and WFIRST after also.
So Euclid is about a 1 meter?
Something like that. This is a smaller telescope. WFIRST after is pretty big for a space telescope. So this is a pictorial version of what Euclid and WFIRST comparison. Euclid is going to be going really wide with smaller number of galaxies per square degrees. That's what WFIRST is sort of going for, smaller, but much, much, much denser. So higher order correlation function. Other summary statistics, people have been looking at voids or filaments. I'll mention a little bit of what we're doing. Galaxies are basically intrinsic aligned. We mentioned these crazy systematics about lensing before, that you need to learn about these intrinsic alignments of galaxies just aligned, whatever. Interesting astrophysics or dynamics problems, but also contamination of any weak lensing you do for that population, right? For any galaxy's population, you need to figure out what the underlying intrinsic alignments they have. Otherwise, you get the wrong answer of how much lensing is happening. So what we're trying to do is that the densely sampled spectroscopic galaxies, such as those in WFIRST, will allow you to reconstruct these filamentary structures. And in principle, you can use this to test different intrinsic alignment models and put a very good constraint on those models that helps really backing out the weak lensing side of the story. And that's it. Thank you very much. I can go back to other points. No questions. I'm perfect. I'm usually not that. Yes.
So for the E of G for Planck crosswalk,
yes.
You're just showing us jackknives and null tests at this point?
What do you mean? You mean this part?
Yeah.
No. This is real data. The error bar is from jackknife or MOX.
Oh, I see.
The error bars. This is actual data points. This is actual signal from actual data.
On your previous slide, we were finding a low cross correlation.
Let me go back to that. You mean this one?
Yeah.
This is the correlations with Planck lensing. This is the correlations with the galaxy itself.
But that's,
it seems
so it's low here, but it's coming out dead on lattice model?
It actually is slightly low. If you look at this plot, it comes out slightly lower, just a little bit, about 2 sigma. But that's very good eye.
So it was much more than 2 sigma on the other one? No?
Well, we also have pretty large error bar from registry distortions. So the error bars, so the plot I show you here did not show you the residual space distortions, right? There are three components to it. One is the galaxy lensing. This is galaxy, and you also need the residual space distortions measurement, which is the one that measures the velocities. That actually dominates the error for this particular analysis. But for photometric, surveys like LSST or maybe CHIME can be possible, then that wasn't the dominating error. The RSD error actually is not as big. Other questions? I saw one hand here.
So what updates in instruments when you go from BOS to EBOS?
Updates in instruments. The BOS to EBOS, actually we didn't have a very strong update on instrument, but a lot of updates on target selections. So that was actually quite hard because you're going to push for much, much dimmer galaxies, like emission line galaxies. And then you're pushing for quasars, which are very hard to target, even in BOS. We were struggling in BOS already. But luckily, we have the WISE telescope, which actually helps a lot in targeting high redshift stuff. And so that helps a lot. And Dezzy Lang, who's actually Canadian, take some force photometry to make sure all these things match up between WISE and SDSS imaging. And that helps to really bring it back. And that's also used in Dezzy, for example, for the target selection. The instrument upgrades is pretty much not much there. But the Manga and Apogee has both instruments changes, but not EBOS. Other questions here?
Yeah, going back to the EAO reconstruction.
Okay.
You mentioned that there are several ways that we can do the reconstruction.
Yeah.
Maybe slightly different answers or different monopoles and protocols.
Yeah, let me show you this plot.
What's the motivation for the different reconstruction techniques? Like, are they trying to optimize various different quantities?
There are different quantities that you can optimize. So the most important criteria is really, unbiased alpha, parallel alpha perpendicular, achievement, which is the distance ratios recovered should be the input. So that's the major metric. But for example, this reconstruction method uses a method that really is not FFT when they construct the potential field. Well, when they construct what they should be moving, they don't take an FFT field. They actually do it by finite differencing. So that takes super long time. Well, this one is a simple, I assume the universe, is pretty much in a 3D box and do FFT on it. That's the other method, for example. And these three lines are different ways of smoothing the field. What is the right kind of smoothing to go from the sparse sampling of the density field to a density field that you hopefully recover?
So just different approximations involved.
Different approximations involved. Recently, Chris Blake has actually written a paper that talks about environmental dependence of how you should be doing BO reconstruction, for example. And that all plays into these discussions. The question is, do you want to mess around with the data more, or do you want to mess around with the theory? So what we were showing here is really we can actually predict it from the theory with the input smoothing lens. But that's for one particular reconstruction method. Because you need to know it has to be a linear approximation, because it's Saldovic approximation. This is the first order. But in principle, it's not bad to try to do it at high order. Tessa and Saliraga also had tried to improve this using these iterative methods, and we didn't see a significant improvement at all. They actually even said in the paper it's like maybe like a 1% to 2% improvement. So in real life, with all the other junk happening, like the survey selection function, the fact the universe is not in a box, it's not helping that much either. Other questions?
Okay, so Shirley will be around for the